Hello, and welcome to Kognito Key. Today we're going to pull back the curtain on a really cool piece of tech, the waveguide. It's kind of like this invisible highway carrying signals for everything from, your microwave oven all the way to deep space communication. We're going to break down exactly how it all works.
So I'm sure you've seen coaxial cables, right? They're literally everywhere. And for lower frequencies, they're great. But what happens when you crank up the speed into the microwave range? Well, they start to act like leaky pipes, just losing all that precious energy. And that's where our hero, the waveguide, comes in. They're built to be this perfect, almost lossless pipeline for these super fast signals.
All right, so how do these things actually work? Here's what we're going to cover in this explainer. We'll start with the high-frequency challenge, introduce the waveguide, see how waves travel inside, figure out how to measure performance, and then wrap up with the pros and cons. Let's get into it.
Okay, first up, the high-frequency challenge. Just to give you an idea, we're talking about signals that are zipping along at insane speeds, somewhere between 300 megahertz and 300 gigahertz. At that kind of speed, your everyday wires, they just can't handle it. They leak energy like a sieve, so for these kinds of jobs, they're pretty much useless. We need something way, way better. And that something better brings us to our hero, the waveguide. It's such an elegant solution, really. So simple, but it solves a really complex problem, making sure those high-frequency signals get where they're going with all their power intact.
So what exactly is this thing? You might be surprised. It's basically just a hollow metal tube, usually made from copper or aluminum. The real magic happens on the inside. You see, the electromagnetic waves bounce off the inner walls, which guides them perfectly along their path. And to make it even more efficient, a lot of the time these walls are coated with a thin layer of gold or silver to reduce any energy loss to almost zero.
Okay, now for the really cool part. How do these waves actually travel inside the waveguide? They don't just flow through like water in a pipe. Nope. They move in these very specific, organized patterns. We call them modes, and they're all about how the electric and magnetic fields are playing with each other. So first up is what we call the transverse electric mode, or TE mode. Here's a simple way to picture it. As the wave is zipping down the tube, its electric field is always pointing sideways, completely perpendicular to the direction it's traveling. The magnetic field, though, it's got a little more freedom. And then, of course, we have the transverse magnetic mode, or TM mode. And yeah, you probably guessed it, it's the exact opposite of the TE mode. In this case, it's the magnetic field that's perfectly sideways, to the direction of travel, while the electric field has some component pointing along the tube.
So that leads to a really important question, doesn't it? We have a TE mode where the electric field is transverse. We have a TM mode where the magnetic field is transverse. So why isn't there a TEM mode where both fields are transverse? I mean, that's what happens in a coax cable. What makes a waveguide so special?
And right there, that's the key difference. This is the whole shebang when it comes to what sets waveguides apart. The crucial point to remember is, a TM mode is just not supported in a waveguide. It's impossible.
Okay, so let's break down why that is. For TM wave to even exist, you need two separate conductors. You need an inner one where the electric field starts and an outer one where it ends. Think about a coaxial cable. It's got that center pin and the outer shield. You also need a current source to get that magnetic field going. But a waveguide is just a single hollow tube. It doesn't have that two-conductor setup, so a TM wave just has no way to form.
All right, so now that we know how the waves move around in there, let's talk about performance. How do we actually measure how well a waveguide is doing its job? There are a couple of key things we look at.
First, there's something called the cutoff wavelength. The best way to think about it is like a size restriction. Imagine a tunnel that has a height limit for trucks. If a truck's too tall, it's not getting through, right? It's the same idea for waves in a waveguide. If the wave's wavelength is too long, meaning the wave is physically too big for the tube, it just gets blocked. It can't propagate. And that brings us to the other side of the same coin, the cutoff frequency. You see, wavelength and frequency are opposites. A longer wavelength means a lower frequency. So what this all means is that for a signal to get through the waveguide, its frequency must be higher than this special cutoff frequency. It's kind of like the waveguide is a bouncer at a club, It only lets the high-frequency signals inside.
Okay, next up is group velocity. Now this can be a little tricky. This isn't the speed of the individual ripples of the wave. Instead, it's the speed of the actual information being carried, the overall package, the message itself. That's what we call the group velocity.
Okay, so we've covered a lot, but the big question is, when should we actually use a waveguide? Just like any other technology, it's got its good points and its bad points. Let's weigh them up. So on the pro side, the advantages are huge. You get almost zero power loss, which is amazing, and they can handle a ton of power. That's why they're so crucial for stuff like high-power radar or satellite transmitters. Plus, the design itself is pretty simple. But on the con side, well, they are expensive to make and install. They're also really rigid, so you can't just bend them around corners. And compared to cables, they can be pretty big and bulky.
All right, let's do a super quick recap of the most important stuff. First, waveguides are what you use for high-frequency signals when regular cables just won't work. Second, they're basically hollow metal tubes that guide waves using internal reflection. Third, they support TE and TM modes, but, and this is a big one, they do not support the TEM mode. And finally, they're super powerful and have very low loss, but they're also costly, bulky, and not very flexible. So that leaves us with one final thought to chew on. Our world is all about signals getting faster and faster, while our devices have to get smaller and smaller. So what's next? What's the next evolution of this simple but incredibly powerful waveguide going to be? It's an interesting question for sure.
Thank you so much for watching Kognito Key. I really hope this gives you a much clearer picture of the amazing world of waveguides. If you found this explainer useful, please do me a favor and hit that like button, share it with anyone you think might be interested, and of course, subscribe to our channel for more deep dives into the tech that makes our world go round.